So for our number 6, we have a bunch of biconditional statements, and we have to check whether these statements are true. So I've put here the truth table for the biconditional, and it is true whenever P and Q have the same truth value. So when they're both true or when they're both false. If they have different truth values, then it's false. And I'm just going to number these rows just so that we can reference them, and that way it's easier. Okay, so let's begin with item A, where P is the statement triangles have 3 sides, and Q is the statement squares have 4 sides. And let's decide the truth values of these. So P is true, right? So we're going to put true here for A. P is true because triangles do have 3 sides, and then Q is also true because squares do have 4 sides. So because P and Q are true, we're going to reference row 1 where we have true and true, and then we can see that the biconditional is also true. So we're going to put a true here, and then I'll just highlight these when we are done, right? So maybe I'll highlight them in purple or something just so that we can get it out of the way. So that one is done. Okay, let's go to the next one. So over here for item B, P is 7 plus 5 is equal to 12. And then Q is 1 plus 1 is equal to 2. So let's decide the truth value of these. So P is true because 7 plus 5 is 12, so that is true. Q is true, 1 plus 1 is equal to 2, and therefore P, if and only if Q is also true, and you can check it on row number 1, right, where we have true, true, and therefore the biconditional is true. I'm not going to highlight it, I didn't like how it looks, so I'll just leave it this way. Okay, what about item C? Well, P is B is even, and Q is B plus 1 is odd. And assume that B is some fixed integer. And the way they tell us to assume that, because if it hadn't been assigned a value, then this would not be a proposition, right? So, okay, we have to now consider 2 cases, right? Because we don't know whether B is even or odd. So we're going to consider case 1, where B is even. And then case 2 is going to be where B, let me just move up, where B is odd. Okay, if B is even, then we have here P. If B is even, then P is clearly true, right? Because B is even, so that's true. What about Q? For Q, B plus 1 is odd. So if B is even, then B plus 1, so whenever we add 1 to an even number, we get odd. So that is true, right? Therefore, P implies Q must also be true by the first row, because we have true and true. Okay, so I forgot to put this previously. That is true, and then this is true. Yeah. Now let's do D. Oh, sorry, we can't put true yet because we didn't do the second case, right? Okay, what case 2, B is odd. So P, if B is odd, then B is even is false, right? So that's false for P. What about Q? B plus 1 is odd. Well, if B is odd, any odd number plus 1 will give us an even number, right? So Q is false. And then the biconditional P implies Q. Now we're going to be at the 4th row of the truth table here. Yeah. So in the 4th, we have F, F, T. So P implies Q is true. So regardless of whether B is even or B is odd, this biconditional is true. Okay, let's go to D. M is odd if and only if M squared is odd. So once more, we do have to consider 2 cases. We don't know if M is odd or if it is even. So let's consider the case 1 where M is odd, and 2 where M is even. Okay, so For m is odd, our p, let's see, our p is highlighted in yellow, m is odd, right? So our p is clearly true. What about our q? So we'll highlight that. M squared is odd. Is the square of an odd number also odd? And yes, it is, right? And the reason that it is, and I'm going to put this in a different color here, is that an odd number is defined as a number that goes like 2k plus 1, where k belongs to the set of integers, right? So as long as k is an integer and you can express it as 2k plus 1, this is the definition of an odd number, so odd. Therefore, if we square this, we're going to have 2k plus 1 squared, which is equal to 4k squared plus 4k plus 1, which is equal to 2 times 2k squared plus 2k plus 1. Now, this 2k squared plus 2k, this is also an integer, right? So this has the form, say, 2w plus 1, where w belongs to the integer. So once more, we do have the form of an odd number, where the remainder is 1 whenever we multiply by 2. So also odd. So let me just remove this. Yeah, so if m is odd, p is true and q is also true, right? Because m squared is going to be true. Therefore, the biconditional is also true. And we have this by row number 1, or true, true, true. Now let's consider the case where m is even, right? So in the case where m is even, then p, m is odd, is clearly false. So p is false, right? What about q? If m squared is odd, right? So in the case where m is even, if m is even, it means that, as we saw previously, m is equal to 2k for some integer k. So when we square this, we're going to get 2 times 2k squared. This is also an integer, this whole thing here. So this is the same thing as saying like 2w, where w is an integer. So the square is also even, right? So q is clearly false because m squared is not odd. So false, and therefore the biconditional here is true, right? By line number 4, where we have false, false, and true. So for this one, I'm going to say that this one is true. Okay, now let's do E. So for E, we have P is 5 plus 6 is equal to 6 plus 5, right? So very clearly true. What about Q? Q, 7 plus 1 is equal to, oops, I did that in the wrong color. 7 plus 1 is equal to 10. Well, that is clearly false because it's equal to 8. So Q is false. And therefore, we are in the scenario of line 2, true and false. And the biconditional is false in this case, right? So false. So we're going to put a false. What about F? So P is a parallelogram, has 3 sides, right? And this one is false because a parallelogram has 4 sides. So P is false. What about Q? Q is 27 is prime. And that one is false because 27 is a power of 3. So false. So right now we have P and Q are both false. So therefore the biconditional is true by line number 4, right? So we can say that this one is true. Let's go to G now, where we have the Eiffel Tower is in Paris. That's our P. So I'm going to highlight this in yellow. Eiffel Tower is in Paris. That's our P. And P is true because it is in Paris. What about Q? Q is if the chemical symbol for helium is H. And that one is false because H is for hydrogen. Helium is He. So Q is false. and therefore the biconditional by line, let's see, true, false, by line number 2 here, in row number 2 we have true, false, false, therefore it is false. So we're going to put a false here. So let's do E, G, actually H, right? Let's do H. So let's identify P first. So P is root 10 plus root 13 is less than root 11 plus root 12. So now if you put this in your calculator, let me put this in and see what I get. If I put it in my calculator, I get that 6.768 is less than 6.781. So that is true. P is true, and you can check that for yourself in your calculator. And what about Q? Root 13 minus root 12 is less than root 11 minus root 10. So when I plug this into my calculator, I'm going to get, let's see, 0.141 for root 13 minus root 12 is less than 0.154, which is clearly true, right? So I have true, true, and therefore my biconditional is true by line number 1. So I'm going to put true here. Let's do I, right? And for P, we have that X is greater than or equal to 0. That's our P, right? Actually, we have to consider two cases for this one, because even though X is a fixed number, we don't know whether it is positive or negative. So let's consider the case where X is positive and also the case where X is negative. So whenever you have these ambiguous cases where the truth value depends on situations, you do have to break it down by cases. So for P, X squared is greater than or equal to 0. Well, this is always true, right? So true. And what about Q? Q is, let me highlight that, X is greater than or equal to 0. Well, in the case where X is positive, this is true. X is greater than or equal to 0. So Q is true, and therefore P implies Q is also true by the, let's see, by the first row. By the first, this first row over here. Now let's consider the case where X is negative, right? So for P, X squared is greater than or equal to 0. This is still true because any negative number squared is positive, right? So this is still true. However, now for Q, it is false, right? Because X is less than 0. It's not greater than or equal to 0. So Q is false, and therefore P implies Q is false. So because we have both cases, and the biconditional is a promise, right? A promise that whenever P is true, Q is true, and also a promise that whenever Q is true, P is also true. So sometimes this promise will be broken, right? So we can't say that it is true because at some points, at some numbers, it is broken. So this ends up being false. So this ends up being false. Okay. Let's go to J, right? So J, P is X squared minus Y squared equals 0. So for this one, we also need to consider two cases, right? But these two cases are either when X is equal to Y, or when X is not equal to Y, right? Actually, and I'm going to put it X squared just because then that takes care of our negative and positive. So case 1, X squared is equal to Y squared, and case 2, X squared is not equal to Y squared. Okay, so P in case 1, if it is equal, right, X squared is equal to Y squared. So when we take their difference, it's going to be 0. So P is true, and Q, X minus Y times X plus Y. Now, X minus Y times X plus Y, we do have a difference of squares. So this is equal to X squared minus Y squared if you FOIL it out. So therefore Q is also true, right? Because Q is the same statement as P, just in an expanded form. And therefore the biconditional is going to be true as well by line number 1. For case 2, where x squared is not equal to y squared, we're going to have that P is, and I should actually highlight our Q over here. We're going to have that P is false, right? Because if x squared isn't equal to y squared, then their difference will not give you 0. So P is false. And because Q is the same statement as P, only in the expanded form, then P is also going to be false, right? So this biconditional statement will be true by the 4th line. And if you guys are, by the 4th line. So in both cases, whether x squared is equal to y squared or whether it is not equal, this biconditional statement is always true. So we're going to put here that that this is true. So now let's consider K, which is the last one, right? So for K, we need to consider 2 different scenarios. Because if x plus, so actually let me scroll this up. So we know that from our basic algebra that x plus y squared does not equal x squared plus y squared, right? We know this. And we know this because x plus y squared is equal to x squared plus 2xy plus y squared. So just a reminder that these are different statements, right? So we have to consider both cases where x plus y squared, x squared plus y squared is equal to 50, right? And where it is not. So case 1, x squared plus y squared is equal to 50. And then we are going to consider case 2, where x plus y squared is equal to 50. Now, these are different things, right? They're not the same things. The only case where they would be the same is if x is and y are, well, no, because then it will be equal to 0, right? So these will never be the same. All right, so let's then get our p's. So our p is x squared plus y squared is equal to 50, right? And our q is x plus y squared is equal to 50. So case 1, if x plus y squared is equal to 50, then p is true, right? And q is false. And therefore, this biconditional statement, P implies Q is, we have true, false, so we're the second row, this is false. Case 2, we have that P is false, because x plus y squared is equal to 50. Q is true, and therefore, P implies Q is false, right? So in both of these cases, we can see that it leads us to false because we'll have different truth values for P and Q. And therefore, we can say that this one is false. So let me just zoom in for you guys so you guys can get the answers to these. And that is it.